Welcome to section 8.1, Sequences and Summation Notation. Objective number 1. Find particular terms of a sequence from the general term. A finite sequence is a function whose domain is the set of the first n positive integers. An infinite sequence is a function whose domain is the set of positive integers. Okay? So finite has a certain number within a set, whereas infinite could be all of the numbers within a set. The terms of a sequence are denoted by the letter A with a subscript representing the term number. For instance, the Fibonacci sequence of numbers is an infinite sequence that begins as follows: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233. The first two terms are 1. Every term thereafter is the sum of the two preceding terms. For example, the third term 2 is the sum of the first and second terms. 1 plus 1 equals 2. The fourth term 3 is the sum of the second and third terms. 1 plus 2 equals 3, and so on. We can think of the Fibonacci sequence as a function. The terms of the sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and 233 are the range values for a function f whose domain is the set of positive integers. So we have our domain 1, 2, 3, 4, 5, 6, 7, and so on, and then the range. So the first term is 1. The second term is 1, the third term is 2, the fourth term is 3, and then so on. Thus, f of 1 equals 1, f of 2 equals 1, f of 3 equals 2, f of 4 equals 3, f of 5 equals 5, and so on. All right, so a subscript 1 would be 1, because the first term within the function is 1. A subscript 2 would be 1 because the second term is 1. A subscript 3 would be 2 because the third term is 2. A subscript 4 would be 3 because the fourth term is 3, and so on. So the notation A subscript n represents the nth term or the general term of a sequence. The entire sequence is represented by the set of A subscript n. So in these examples, we're going to write the first 4 terms of the sequence whose nth term or general term is given. So these are going to be considered finite sequences because we're only looking at the first 4 terms. Let's do the first one. A subscript n equals n squared plus 5. So we need to find the first 4 terms. So the first term would be when n equals 1. So we're going to substitute in 1 for n. So we'll have 1 squared plus 5. That's 1 plus 5, which equals 6. And we'll take 2, substitute that in. That's 4 plus 5 equals 9. And we'll take 3. That's 9 plus 5 equals 14. and then we'll take 4 and substitute 4 in. 4 squared plus 5, that's 16 plus 5 equals 21. So our first 4 terms would be 6, 9, 14, and 21. Okay, let's do the next one. A subscript n equals 3 times negative 1/3 to the power n. So we'll find the first term by substituting in 1 for n. And then the second term, substituting in 2 for n. The third term, substituting in 3 for n. The fourth term, substituting in 4 for n. And so now we can simplify each of these statements. So we'll have 3 times negative 1/3, which would equal negative 1. Then we'll have 3 times a positive 1/9, which would equal 3/9, which will equal 1/3. We have 3 times a negative 1/27. So that would be negative 3/27, which simplifies to negative 1/9. Then we'll have 3 times 1/81, which is 3/81, which simplifies to a positive 1/27. So our first 4 terms are negative 1, 1/3, negative 1/9, and a positive 1/27. Let's make that the same squiggly brackets. There we go. Our third one, a sub n equals 2 times n plus 5. Again, we're trying to find the first 4 terms in the sequence. So we'll substitute in 1, then we'll substitute in 2, then we'll substitute in 3, and then we'll substitute in 4 into the formula. So we'll get 2 plus 5, which is 7, then 4 plus 5, which is 9, then 6 plus 5, which is 11, and 8 plus 5, which is 13. So our sequence is 7, 9, 11, and 13. Okay, so those are the first 4 terms in this sequence. And then number 4. Okay, so we want to find the first 4 terms in this sequence. So we will substitute in 1 wherever we see an n. So I like to set up my formulas for each term. That way I can simplify each expression. Okay, so now that I've set each one of them up, I can now simplify. Okay, so I have negative 1 and then 2 plus 1. So that will be negative 1/3. Then I'll have a positive 1. Then 4 plus 1, which is 1/5. 1/5. Then I'll have negative 1/8 plus 1. So that's negative 1/9. Then I'll have 1/16 plus 1, which is 1/17. So the first four terms in the sequence are negative 1/3, 1/5, negative 1/9, and 1/17. All right. So notice that the terms of the first sequence in number 2 alternate signs. Such a sequence is called an alternating sequence. The alternation in signs can be represented in the nth term by a factor of negative 1 raised to a variable power that alternates between an even and odd integer. For example, a sub n equals negative 1 to the power n would represent odd number terms that are negative and even number terms that are positive. Now, if we have b sub n equals negative 1 to the power n plus 1, this would be odd number terms that are positive and even numbered terms that are negative. So the recursion formula defines the nth term of a sequence as a function of one or more terms preceding it. So let's look at two examples here, and we're asked to write the first four terms of the sequence defined by each formula. Now, the difference between these examples and the previous ones is that in these examples, we are given a value for the first term in our sequence. So we're going to use that value in order to find the subsequent terms in the sequence. So let's do the first one. So a sub 1 is 3. And our formula is a sub n equals 4a subscript n minus 1 minus 2. So we need to find a sub 2, we need to find a sub 3, and a subscript 4. Okay, so let's set up our formula. So 4 times a subscript n, in this case it's 2 minus 1, and then we're going to subtract 2. So this would be 4 times a subscript 1 minus 2. Well, we know what a subscript 1 is, 3. It was given to us. Oops, I forgot to do minus 2. Minus 2. Minus 2. So that would be 12 minus 2, which equals 10. So the second term in this sequence would be 10. Let's do the next one. 4 times a subscript 3 minus 1 minus 2. So 4 times a subscript 2 minus 2. Well, a subscript 2, so the second term in the sequence, times 4 would be 4 times 10 minus 2. So that's 40 minus 2, which equals 38. And our fourth term, a 4 minus 1 minus 2, there we go. So that would be the third term in our sequence, times 4. So 4 times 38 minus 2. So that's 152 minus 2, which equals 150. So the first four terms of the sequence would be 3, 10, 38, and 150. For 6, Our first term is given to us, that's 3. And our formula is a subscript n equals 2 times a subscript n minus 1 plus 5 for all n values that are greater than or equal to 2. Okay, so n must be greater than or equal to 2 in order for this formula for our sequence to exist. So we know our first term. We need to find the next 3 terms. So let's substitute in our value for n, and then plus 5. So we'll have 2a. I'm just setting each one up by just substituting in my value of n, knowing that I'm going to need the previous value in order to find the current one. So for a subscript 2, we'll have 2 times a subscript 1 plus 5. So that will be 2 times 3 plus 5, which is 6 plus 5, which is 11. Then for a subscript 3, we'll have 2 times a subscript 2 plus 5. So that's 2 times 11 plus 5, which is 22 plus 5, which is 27. Then we'll have 2 a subscript 3 plus 5. So that's 2 times 27 plus 5, which is 54 plus 5, which is 59. So the first 4 terms in this sequence are 3, 11, 27, and 59. All right. Objective 4. Use summation notation. So the sum S of the infinite sequence A subscript n equals A subscript 1, A subscript 2, A subscript 3, and so on, is called an infinite series and is represented by S equaling A subscript 1 plus A subscript 2 plus A subscript 3, and so on. The sum of the first n terms of the sequence is called the nth partial sum of the sequence and is denoted by S subscript n. The nth partial sum of a sequence is a finite series. The Greek letter sigma is used to represent summations. So S subscript n equals the summation of A subscript I, where n is the upper limit of the summation, I is the index of the summation, and 1 is the lower limit of the summation. Okay, so just like we did in the previous problems where the directions told us to find the first 4 terms, your summation here will tell you where you're going to start and where you're going to end. So here we will start at 1 for I, in this case it's I, and we will go all the way up to n, whatever value n is. So the sum of all terms in the sequence is an infinite series, and it's given by the summation of A subscript I, where I is equal to 1, and you're going all the way to infinity. So any letter can be used for the index of the summation. The letters I, J, and K are used commonly. The lower limit of summation can be an integer other than 1. So it could be 2, 4, 7, 8, whichever one. Then we write out a sum that is given in summation notation. We are expanding the summation notation. Okay. So here we have some of the properties of summation notation. We have the first one dealing with multiplication. So when you have a constant c being multiplied by your a subscript I, you are multiplying each term in the sequence by 3. So you can multiply each term that you find in the sequence by 3 and add it together, or you can add all of your terms together and then multiply by 3. Either way works. For number 2, you can find the terms of A and B in your sequence, add them together as pairs, or you can break it up into 2 different summations and then add them together. And similarly for subtraction as well. You can split them up, just making sure that you multiply this negative value by each term in your second sequence. So B subscript I. Okay, that's very key between number 2 and number 3. So here we're going to write the terms for each series and then find the sum. Okay. So let's do the first one, number 7. All right, so our variable here is k for this summation. We are starting at the first term, number 1, and we're going to go all the way up to 3. Okay. So we are adding each term together. So the first term would be 3 times 1 minus 8. So whatever this expression equals will be the first term. And we're going to add it to the second. So 3 times 2 minus 8. And then 3 times 3 minus 8. Okay. So we'll have 3 minus 8, which simplifies to negative 5, plus 6 minus 8, which simplifies to negative 2. And then we'll have 9 minus 8, which simplifies to 1. So the sum of all 3 of these terms would be negative 6. Okay. Next one. All right, the summation of 2i divided by I squared. We're starting at the first term, number 1, and we're going all the way to 4. So our first term would be represented by 2 times 1 divided by 1 squared. The second term would be 2 times 2 divided by 2 squared. The third term would be 2 times 3 divided by 3 squared. And the fourth term would be 2 times 4 divided by 4 squared. So when we simplify, we'll have 2 divided by 1, that equals 2. And then we'll have 4 divided by 4, that equals 1. Then we'll have 6 divided by 9, that equals 2/3. And we'll have 8 divided by 16, that equals 1/2. Okay. So when we add all of these values together, we will have 25 over 6 as the summation of all the first 4 terms in this series. All right, number 9. Okay. So we have negative 1 to the power j plus I times 3 times j. Okay. We are starting at the third term and we're going all the way up to 5. So that means we're only adding 3 terms together. So we'll start at the third term, so 3 plus 1, and then 3 times 3, and then we'll add it to the fourth term. So wherever I see a J, I'll be adding 4. Oh, that should be a bracket. Now I'll just rewrite it so it's cleaner. There we go. And then the fifth term. So 5 plus 1 times 3 times 5. All right. Now we can simplify. So in our third term here, we'll have negative 1 to the fourth times 9. And that simplifies to 9. Then we'll have negative 1 to the fifth power times 12. And that will simplify to negative 12. And then for the third term here in our sequence, we'll have negative 1 to the sixth power times 15. And that will simplify to 15. So 9 plus negative 12 plus 15 would get us 12. Okay. All right. Number 10, we want the summation of 10 where we start at 1 and we go all the way up to the fourth term. So the first term is going to be 10. The second term would be 10. The third term would be 10. And the fourth term would be 10. So our summation of the first four terms would be 40. There's no value being there's no n being multiplied to 10. So the expression for each term in the sequence is going to be 10. All right, let's do a couple more. So here we're asked to write the terms of each series and find the sum. Okay, so we're continuing on from the previous couple of problems. Let's do number 11. So our summation expression we're adding together is I squared. We're starting with number 1 and we're going to go all the way up to 4. So we'll have 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's 1 plus 4 plus 9 plus 16. And so that equals 30. Awesome. Let's do 12. So we have j plus 1 squared. So we're going to start at 0 this time for our first term in this series. And we're going to go all the way up to 3. So we'll have 0 plus 1 squared plus 1 plus 1 squared plus 2 plus 1 squared plus 3 plus 1 squared. So that will give us 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's 1 plus 4 plus 9 plus 16. We know that equals 30. Interesting. Let's do 13. So our expression here is k minus 1, that quantity squared. We're starting for this one at the second term, and we're going to go all the way up to 5. So we'll have 2 minus 1 squared plus 3 minus 1 squared plus 4 minus 1 squared plus 5 minus 1 squared. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's 1 plus 4 plus 9 plus 16. That also equals 30. So the last three problems that we did all equaled 30. To be honest, they all came down to 1 plus 4 plus 9 plus 16. So something that we can note is that the sum may be written in many different ways to get us the same result. So we just did 3 different problems whose summation formula were all different, but they all gave us the same value, 30. To be honest, they all gave us the same values for each term, which then summed to 30. Okay, so you can have different expressions represent the same sum. All right, so now for these examples, we're going to work backwards. We're now going to write each sum using sum notation. So we need to identify what is the pattern and relationship going on between each of these terms that will allow me to write my sum notation. So let's look at the first one. We have 2 over 5 plus 4 over 5 plus 8 over 5 plus 16 over 5 plus 32 over 5. The first thing I noticed right off the bat is the denominators are all 5. Okay. The second thing I notice is my numerators have a pattern going on. I'm going 2, 4, 8, 16, 32, and these are all products of 2. For example, 2 is 2 to the first power, 4 is 2 squared, 8 is 2 to the third power, 16 is 2 to the fourth power, and 32 is 2 to the fifth power. Okay? So if I were to set up my summation, right, I would take 2 to the power n over 5. Okay? Where my first term is 2, my second term would be 4, third term 8, and then so on. So n is going to start at 1, and we're going to go all the way to the fifth term. So this would be our summation notation for this series. Let's do the next one. 1/2 plus 1 plus 2 plus 4 plus 8. Okay. What's going on? Well, I go from 1/2 to 1, and then 1 to 2, and then 4, and then 8. Well, I know that anything to the 0 power equals 1, and then 2, 4, and 8 again are products of 2. So I know 1 would be 2 to the 0, and then 2 would be 2 to the first power, 4 would be 2 squared, and then 8 would be 2 to the third power. So 1/2, negative exponents. So this would be 2 to the negative 1. Okay, so I can set up my sum notation. I would be 2 to the, well, it can't be 2 to the n because the first number in my sequence is 1/2, so that's 2 to the negative 1. So my first term should be negative 1. How am I going to do that? Let's see. Well, I can represent this by n minus 2. Okay, so if I plug in 1, my first term in my sequence, I want it to be 1. Oh, sorry, not 1. I want it to be negative 1. So if I plug in 1 into n minus 2, I'm going to get negative 1. Okay, so this is similar to the recursion formula that we did near the beginning of this section. So n minus 2 would represent the first term, 2 to the negative 1. And then I know I'm going to start at 1. And then I'm going to go all the way up to 5. Because if I plug in 5, 5 minus 2 would get me 3. Because I have 5 terms. Okay. Awesome. That one was a little tricky, but we got it. All right, 16. 1 squared plus 2 squared plus 3 squared, all the way up to 9 squared. Okay, so this one is a little bit easier to see. So for our summation, we know we're going to have 9 terms, and we're going to start with 1. Okay. Now, our first term, when we plug in 1, is 1 squared. The second term, when we plug in 2, is 2 squared. So we know we're going to take n and then square it. All right. 17. We have negative 2/3 plus 4/9 minus 8 over 27 plus 16 over 81. Okay, so first thing I notice is that signs are changing. I have negative and then positive and then negative and then positive. Okay. And then the next thing I notice is all of the numerators, again, are products of 2. And then all of the denominators are products of 3. Okay. So I know in the numerator, I'm going to have 2 to some power. Okay? And then the denominator, 3 to some power. So in other words, I'm going to have 2/3 to some power. Okay? Because 2 is 2 to the first power. 3 is 3 to the first power. And then 4 is 2 squared, 2 to the third, and 2 to the fourth. And similarly in the denominator as well. Okay. So I know that this would be the expression to represent the fraction. Now I just have to figure out the signs. Well, for the first one, 2/3, the power is 1. So if I have a negative value and I take it to the first power, it's going to be negative. Okay, now let's check the second one. So the second one would be 2/3 squared, which will be 4/9. And if I square negative, my answer will be positive. Okay, so if I have a power that's odd, my answer will be negative. If I have a power that's even, my answer will be positive. So that works. So I will have my expression -2/3 to the power n, where n starts at 1 and we go all the way to 4. Now, I could have represented this as, let me set my summation up. Okay, I could have represented this as -1 to the power n times 2/3 to the power n. Okay, I could have represented it this way, where I separate the negative value from the fraction 2/3. Because I know if I multiply anything by a -1, it's going to be positive. So whichever way you see it more clearly works. Okay. All right, and 18. So we have 1 plus 1/2 plus 1/4 plus 1/8 plus all the way up to 1/2 to the power n minus 1. Now this one is special because they give you the expression that you're going to use at the very end, which is great. Now this is a summation where you're going to go to infinity. Okay. So, or in this case, all the way up to n, whatever n is in the problem. Since they didn't tell us n, we're going to go all the way to n, and we are going to start with 1. We're going to start with 1. So, I have to change my value here, actually, and my expression to another variable. Let's use I, and we're going to start at 1. Okay. So this one's special because they give you the expression already in the problem. You're going to start with your first term and you're going to go all the way up to n, whatever n is in your specific problem. So this is really nice. All right. And it's a great way to end section 8.1.